Welcome to this explainer. Today, we are going to completely transform the way you tackle defects and waste in complex engineering projects using the absolute powerhouse methodology that is Lean Six Sigma. As engineers, we naturally just want to dive in and fix things, right? But without hard data, we often end up fixing the completely wrong things. So if you've ever felt like your team is just constantly putting out fires instead of actually preventing them, well, you are definitely in the right place. Today, we are going completely data-driven. So let's start with a really hard truth. Why do so many process improvements ultimately fail to move the needle? Usually, it's because standard unstructured engineering fixes, or those quick Band-Aid CAD redesigns, they fail because they treat the symptoms rather than the actual root cause of the process waste. Basically, we guess at the solution, and then we wonder why our costs keep creeping up and our customers keep complaining. It is definitely time to stop guessing and start systematically engineering our solutions.
Okay, let's dive right into this. DMAIC is the specialized weapon your engineering team needs to bring order to the chaos and get profitability back on track. It was born from the minds at Motorola, and it's rooted in decades of statistical analysis. DMAIC is really the foundational life cycle of Lean Six Sigma. It stands for 5 sequential, highly structured phases: define, measure, analyze, improve, and control. And its entire purpose? To relentlessly identify inefficiencies, reduce variation, and eliminate defects until there's practically nothing left to fix.
To see exactly how this works in action, we're going to walk through 6 key steps today. First up, engineering the perfect process with the real-world case study. And then we'll hit the 5 phases: define, measure, analyze, improve, and finally, control. Let's get into it.
Section 1. Engineering the perfect process, the Evercool case study.
So, meet Evercool. They manufacture commercial air conditioning units, and right now, they are facing a massive engineering crisis. Their existing customers, people whose units have broken down, are waiting weeks just to get replacement parts. Now, if you've ever waited for a critical component, you know that kind of downtime is agonizing. It's entirely unacceptable. In Six Sigma, we call this the cost of poor quality, or COPQ. Because of this poor service, Evercool is losing 3 customers every single month. That creates a staggering cost of poor quality equal to over $1.4 million in lost revenue annually. They have to fix this, and they have to fix it now.
Phase 1. Define scope, the problem.
In this initial step, an interdisciplinary team gets together to create a project charter. The team's stated goal is a 30% reduction in the fulfillment cycle. But notice what they explicitly excluded here: new AC unit orders. By drawing a really hard line in the sand and focusing strictly on the engineering and fulfillment of existing replacement parts, they ensure the project is actually achievable, especially given their strict 3-month timeline and having just 3 dedicated staff members on the job.
Phase 2. Measure. Quantify the process. Look, before you can fix a process, you've got to know exactly how it's currently performing. So the team maps every single current input and output. They often use what's called a SIPOC diagram for this, that tracks suppliers, inputs, process, outputs, and customers. Then, by tracking delays over a 15-week period, the team builds an ordered Pareto chart. This visual summary is a total game changer because it reveals they don't actually need to fix everything at once. By addressing just the top categories, specifically supplier defects in compressor valves and failed pressure tests, they can resolve a whopping 83% of the total delay problem.
Phase 3. Analyze. Find root causes.
Now, to locate the exact source of the issue, the team conducts a Gemba walk. That means physically going out and observing the factory floor and the bottlenecks firsthand. Lean Six Sigma demands that we move way past surface-level excuses. For example, if someone says, well, it's taking a long time because we're super busy, that is just a symptom. It's not a cause. We have to drill down to the fundamental structural failures. These analytical tools ensure we aren't just slapping a temporary patch on a much deeper wound.
One of the absolute best tools for this is the 5 whys technique. The team repeatedly asks why to literally peel back the layers of the problem. Why is there a delay? Because orders take too long. Well, why do they take so long? Massive backlogs. Why are there backlogs? Because we can't clear them. Why can't we clear them? Ultimately, if you ask why enough times, you uncover the real structural root cause. In this case, there is absolutely no engineered, standardized procedure for fast-tracking emergency parts through quality control. That lack of procedure was the real bottleneck holding up millions of dollars in inventory. Phase 4. Improve. Implement the fix. Armed with that proven root cause, the engineering team brainstorms targeted solutions and runs small-scale pilot tests. To make sure their new fixes don't accidentally create a whole bunch of entirely new problems, the team utilizes specialized tools like failure mode and effects analysis. This helps them anticipate failures before they even happen. They also implement poka-yoke. This roughly translates to mistake-proofing. It means designing physical safeguards, like uniquely shaped connectors that can literally only be plugged in one specific way, so it becomes virtually impossible for staff to assemble a part incorrectly.
And the definitive, statistically validated proof of success here is just amazing. The baseline data showed the old fulfillment average was 8.67 days. But by eliminating those root causes they identified, the new fulfillment cycle dropped to exactly 6 days flat. Evercool completely shattered their initial 30% reduction goal. This intervention was a massive, massive success.
Which brings us right to our fifth and final phase: control, sustain the results. Listen, any process improvement project that fails to establish a long-term monitoring system is essentially an unfinished project. We have to guarantee that our fancy new 6-day cycle doesn't slowly creep right back up to 8 days over the next year. To do that, the team establishes a formal control plan. By taking periodic samples of the fulfillment times, they map the ongoing average against an upper control limit and a lower control limit on a control chart. As long as those data points stay bouncing between those lines, the process is stable. But if delivery times slip out of bounds, boom, it triggers an immediate alarm for corrective action.
And hey, just to totally round out your Lean Six Sigma toolkit, keep this critical distinction in mind. DMAIC, which we literally just walked through, is heavily focused on fixing an existing broken process to reduce and eliminate defects. However, if your engineering team is tasked with designing a brand new product, service, or process totally from scratch, you'd use its sister methodology, DMADV. That stands for Define, Measure, Analyze, Design, and Verify, and its goal is to prevent defects entirely from day one. By strictly following Define, Measure, Analyze, Improve, and Control, you don't just guess at solutions anymore. You systematically engineer them. You take raw data, you uncover the true structural failures, and you implement mistake-proof processes that actually last. So I want you to take a hard look at your own workflows. What hidden inefficiencies are quietly eating away at your revenue right now? And which engineering process are you going to target with DMAIC first?